Hello everyone. Welcome to Performing Network Analysis with Python. My name is Melinda Morang.
And I'm Max Stone.
We're both product engineers on the Network Analyst development team. In today's presentation, we'll show how you can automate your network analysis workflows and extend the capabilities of ArcGIS with Python. Before we get started, we realize it can be quite difficult to follow along with code in a presentation like this. So all of the code, as well as these slides, are available for download at this address. Go ahead and take a moment to make a note of it, and we'll show it again at the end in case you miss it. In today's presentation, we'll first give a brief introduction to Network Analyst. Then we'll talk about network analysis with Python in ArcGIS Pro, including the new arcpy.nax solver classes. Then we'll talk about the arcpy.nax Network Dataset class. And then finally, we'll talk very briefly about network analysis using web services with the ArcGIS API for Python. So let's begin with a brief introduction to Network Analyst. The ArcGIS Network Analyst Extension is the part of the software that's for solving transportation analysis problems. There are tools for assessing the coverage of different facilities, like service area, for optimizing things like site location with location allocation, or optimizing fleets of vehicles with the vehicle routing problem solver, and for point-to-point routing. For example, with the route solver, you can answer, how do I get from point A to point B? And with the closest facility solver, you can answer the question, what is the closest facility? And you can also solve origin-destination cost matrix problems. Underlying all network analyst workflows is a network dataset. This is the dataset that includes street features and also attributes describing travel times and distances, restrictions for travel, etc. When you perform an analysis, you have to choose which network you want to use to perform the network analysis calculations. Where do I get a network dataset? You can purchase StreetMap Premium, which includes a high-quality network dataset for your selected country or region. You can also purchase StreetMap Premium Custom Roads, which includes the StreetMap Premium data as well as the flexibility to add in your own roads into the dataset. So if you have private roads or something, you can do that. You can build your own network dataset using your organization's data. There's some help available if you're a local government trying to build a network dataset from your street center lines. You can also use other data sources, such as Tiger or OpenStreetMap, although the data quality often isn't that great, and it does require quite a bit of work to get it into a state where it can be effectively used for routing. Also, you might not need your own network dataset at all. You can use the ArcGIS Online services to perform your network analysis calculations. Those services use the same data as the StreetMap Premium product, but you don't actually have to own this data. You just pay service credits and let the servers do the work for you using the data that lives there on those servers. With that, let's move on to talk about how to do network analysis with Python in ArcGIS Pro. The best way to do network analysis with Python in ArcGIS Pro is to use the arcpy.nax module. This Python module provides easy-to-use classes and methods for performing network analysis and accessing the network dataset. This module was added in ArcGIS Pro 2.4, and it's not available in ArcMap. If you've worked with Network Analyst in Python in the past, you might be wondering what happened to arcpy.na. That module is still there, and it still works. However, at ArcGIS Pro 2.4, we added the new arcpy.nax module, and this module makes network analysis faster, and the syntax for using it is more Pythonic. In this example here, I solved a simple service area calculation with both modules, arcpy.na and then arcpy.nax. So for the first solve with arcpy.na, it took about 11 seconds. Then, with the same analysis, same input, same data, using arcpy.nax, the runtime was under 2 seconds. So you can see we've got some significant performance improvements available for you, and we really recommend using this new module when you're performing network analysis with Python in most cases. You'll still need to use arcpy.na if you need to work with network analyst layers, if you're going to publish a map service with network analysis capabilities, or if you need your script to be compatible with older versions of ArcGIS Pro. There's some documentation available that explains this in more detail and helps you make the right choice. But for the rest of this presentation, we'll be focusing on the new capabilities in arcpy.nax. So let's dive into arcpy.nax. This is a summary of the workflow that you'll use for performing a network analysis, such as calculating a route or a service area. So first, you initialize the analysis object, and this is based on a specific network data source. Then you set the properties for the analysis, load the inputs, and then solve the analysis. And then you can access and work with the results. Each type of network analysis or solver has its own Python class. When you instantiate the solver object, you need to set the network data source. This can be either a network dataset or a URL to a service such as ArcGIS Online or a service running on your own portal. Note that while the arcpy.nax module was added in ArcGIS Pro 2.4, URL support for the network dataset source was added in ArcGIS Pro 2.5. Once you instantiate the solver object class, you can set the various analysis properties. You can see a long list of available properties for service area here, such as the travel mode and various properties for fine-tuning the output polygons. The class has methods for loading data and solving, as well as some other helper methods. And when you solve the analysis using the solve method, it creates an instance of a result object for the particular solver. You can access the analysis results from that result object. Now I'll hand it over to Max, and he'll show you a demo of this basic arcpy.nax workflow.
Okay, thank you, Melinda. So I'm excited to show you some demos using the next generation Python API for network analysis, which we call it the Next module. To me, it is a better designed API, easier to understand, and more Pythonic. And also you get the better performance. So now let's jump into one of the scripts that I wrote. So for the first demo, I'm going to show you a simple route workflow, and I will debug to show you the 5 steps Melinda just mentioned. So let's get the debugging started. So here, our network dataset comes from a file geodatabase, and our stops comes from a feature class. And these are my 3 stops, and I just want to find a route that travels through these 3 stops, a very simple routing problem. So to solve this analysis, first, we initialize our route object based on our network dataset. And then you set your analysis settings. So one of the most important analysis settings you might want to set is your travel mode, because it models how your vehicle travels on the network. So to do that, we can get the travel modes from my network dataset. So it returns you a dictionary where the key is the travel mode name and the value is the travel mode object. So from this dictionary, we can get the driving time travel mode. Next, we can set our route travel mode property to be this travel mode object. So this is the second step, set your analysis settings. The third step is to load your data. So you simply call the load function. And the first parameter is an enumeration of route input data type. And we load the stops feature class into the internal stops. So throughout this Next API, you will see that we use the enumerations a lot. And enumeration is just a set of symbolic names representing some constant value. And we use these enumerations just because it makes it easier to use and to understand. So this is the third step, load your data. The fourth step is to solve your analysis. Simply call the solve on your route object. And what it returns, as Melinda showed you on the diagram, is it returns you a result object. And once you get the result object back, you have the property to check whether the solve has succeeded. And if it has succeeded, you can export the routes into an in-memory feature class. Here, we are also using an enumeration of route output data type of routes. And if it's not succeeded, we can export all the messages. So once we get our feature class, we can do a searchCursor. This is a generic ArcPy searchCursor, and it's already out of network analysis, to access the internal feature class and see what we get for our route name and the total kilometers. So we can loop through our in-memory feature class, and on the terminal on the right, we can see the route goes from downtown depot to North Bay depot, and the total distance is 48 kilometers. So this demo shows you the 5 steps that we do this analysis. Create your solver object, set your analysis settings, load data, solve, and export the result. So before I switch over to Melinda, one more thing I want to show you is beginning Pro 2.5. We have added the support to initialize your route object from a portal URL or your ArcGIS Online. So here, I simply switch the network data source to be my ArcGIS Online, to a URL to my ArcGIS Online. And let's get it started. So what now it is doing differently is it initializes my route object based on my ArcGIS Online. So it's using my routing service to calculate my route. And it still gets the travel mode from my ArcGIS Online. So we are setting the driving time travel mode from my organization. And everything else stays exactly the same. We designed this API so that it works seamlessly with local network dataset, or with ArcGIS Online, or with your own portal URL as well. So here we get our result back. In the terminal, the route is from Downtown Depot to North Bay Depot, and the total distance is slightly different than the one that we previously solved, because now we are using our online services, and the data is different than your local data. Okay, back to you, Melinda.
Thank you, Max. One of the most important parts of your network analysis is loading inputs and accessing outputs. There are a couple of ways to do that, and the right choice depends on your situation. I'll summarize these now, and then I'll talk about some of them in more detail later. For loading inputs, you have a choice between loading an existing feature class using the load method, as Max just showed you, or directly inserting inputs using the insertCursor method. For accessing outputs, you can export the result to a feature class using the export method, which is what Max just showed in his demo, or you can directly access the outputs using the searchCursor method. If you want to debug problems with your analysis in the map, you can use save as layer file, and then add the layer to the map in ArcGIS Pro. If you want to create a zip file containing route data suitable for use in Navigator, you can use the save route data method. The solver objects have various types of inputs and outputs, and each of those has a particular schema. For example, service area inputs include facilities and optional barriers, and the outputs include polygons, lines, and a copy of the facilities. Each of these has a specific schema. You can read more about these in the documentation, and there's a link here included in the slide. If your inputs are already in a feature class, the easiest way to use them in the analysis is probably with the load method. If you have fields you care about in the input feature class, you'll need to use the field mappings method to create a field mapping object so you can associate the field names in your input data with the field names used by the schema for the network analysis. For example, the vehicle routing problem solver's input orders class has a field called service time. This field specifies the amount of time that the driver will need to spend at each location. For example, if the driver is making a delivery, the service time is the time to make the delivery. However, that field in your input table might not be called service time, but might instead be called something like delivery delay. You can use field mapping to map your delivery delay field into the VRP order class's service time field. Again, you'll want to take a look at the documentation to see what inputs are supported for the analysis that you're using. For accessing outputs, the result object's export method is quite straightforward. It basically just saves the analysis results to the feature class you specify, and it includes all the output fields. The schema for these outputs is also defined for each output of each analysis type. You can learn more about that from the same link that we showed on the previous page. So now I'm going to hand it over to Max, and he'll show you an example of using load with field mappings with the vehicle routing problem solver.
Okay, thank you, Melinda. So this demo solves the vehicle routing problem. I'm now going to debug this one, so let's get it started. So the first step is to initialize our vehicle routing problem solver. And one thing I did differently in this demo is I first make a network dataset layer, and then I use the network dataset layer name to initialize my vehicle routing problem solver object. And this is the performance trick we want you to adopt. And also, Melinda is going to explain why this improves the performance later in her slides. Next, we set our analysis settings. Here, we want our distance units to be miles and time units to be minutes, because we want our inputs and outputs to be in these units. And we want to visualize our vehicle routing problem route result, so we set the route shape type to be true shape. And we also want to visualize the stops, so we set return stops shape to be true. Here, we load our inputs data, orders, depots, and routes from the file database. So in a real-world scenario, this might be where you want to connect to an external information system, where you get the orders, depots, and routes for the day, and then you fit into the vehicle routing problem solver and find which orders should be assigned to which route, and then after you get the result back, you can update the external information system with the order assignment. So here, to simplify the demo, we get all the inputs and outputs into file geodatabase. Next, we load our orders, depots, and routes into the VRP. So on your input data, you have the delivery delay, and on our internal orders, we have the service time. And Melinda already explained they mean the same thing. So on any of the solver object, you can call the field mapping to get the field mapping for any of the input data. So here, we are asking the vehicle routing problem solver object to give us the field mappings for the orders. So what it returns is a dictionary, where the key is the field name and the value is the field mapping object. So once you get the field mapping object, for example here for the service time field mapping object, we can set the mapped field name and the default value. So we have our data schema and we don't know your data schema, so that's why we need to use the field mapping to map your data into our data schema. So this service time is an internal field on the orders, and if you want to know more about our internal fields, you can read our doc. So here we are setting the service time to map to the delivery delay, and if there is any delivery delay that is missing from your input data, we are setting the default value to be 10 minutes. So essentially we are setting the service time to be 10 minutes by default. And here we know it's 10 minutes instead of 10 hours because we have already set our time units for this analysis to be minutes. So when we load our data, we can use the field mapping for our input orders. And then we solve. Once the solve succeeded, we can export the result. So in some of the workflow, you might want to solve your analysis in one of the application, but then your worker might want to use them in the field. So to complete this workflow, what you can do is you can save the route data as a zip file. So essentially, this zip file will contain a geodatabase with all the route information. And once you get this route data zip file, you can then call share as route layer to share a route layer as a route layer item on your portal. And then when your field worker is using an Esri Navigator app, they can connect to your portal and get this route layer into their navigator and begin routing using the pre-planned route. So here we can see this is our route layer. And to save us a little bit of time, I have already opened it here. So this is a route layer item in my ArcGIS Online account. We can open it in Map Viewer. And we can see this is our route layer. And you can also open it up in your Esri Navigator app to begin routing. And also, let's see our result in ArcGIS Pro. So here is my assigned stops and routes. And this is the route, how do we visit all the stops, and what is the sequence that we visit each of the orders. Okay, back to you, Melinda.
Thanks, Max. If you're getting your inputs from something other than a feature class, such as a CSV file with latitude and longitude, or the results of some other analysis, you can directly insert those into your network analysis using the solver object's insertCursor method. This method isn't the same as the arcpy.da.insertCursor, but it behaves in a very similar way. The searchCursor method on the result object can be used to directly access the outputs. It's very useful if you only care about a couple of output fields. For example, in an OD cost matrix analysis, maybe you just need the travel time between each origin and destination, and you're going to post-process that into some other format. You don't need to write the entire results table to disk just to get that one field. searchCursor is a method on the solver result object, and you can choose which fields to access, and then iterate over the results. It's not the same as the arcpy.da.searchCursor method, but it's very similar. Now I'll hand it back to Max, and he'll show you a demo of using cursors.
Okay, thank you, Melinda. So here I have two demos to show you how to use the cursors. And let's get the first one started. So here, what I want to solve is a very simple route. I have my home coordinates and my work coordinates. I just want to find a route from my home to my work, and I want to get directions. So to solve this problem, here I initialize my route object, still using the network dataset layer name. And then I want to leave now, so I set the route time of day to be now. And then I want to return directions. Now, we open an insert cursor on our input data type of stops, and we just want to insert the name and XYs for each of the stop. So here, we call insert rows twice to insert our home with XYs and work with XYs. Then we solve. Once the solve succeeded, we can open a searchCursor on our directions output to get the arrive time and directions text, and we print out in the console. So on the right side, we can see that we start from home and now and finish at work with turn-by-turn directions. So think about it. If you don't have this insert cursor and search cursor, how would you do this workflow? You will probably turn your data, your input home and work, into some kind of table, and then turn this table into a feature class. Once you have the feature class, you can use the load method that I showed you in the previous demo. And once you get your output, you can export into a feature class, and then you can open a search cursor on the output feature class to get all the values. By using the insert cursor and search cursor directly on the solver object, will simplify the workflow. That's why we designed these search cursors and insert cursors to work with your inputs and outputs, so it's easier for you to use. So the next demo is very similar. Here, instead of only getting one route, I have a couple hundred stops that lays around in San Francisco. And my stops comes from this address as San Francisco CSV, where I have the longitude, latitude, and the street name. So I just want to get the time and distance between each of the stop pair. So this is a typical origin-destination cost matrix problem. So to solve this problem, let's first get it started. So here, we initialize our origin-destination cost matrix solver object. Then we set our analysis settings. If we were to lay all the addresses on the map, this is my addresses. So they are pretty close to each other. And we want to get the time and distance between each of the stop pair. So here we set our time settings and distance settings to be seconds and feet because they are pretty close to each other. And then we open two insert cursors, one on the origins, one on the destinations, with only name and XYs. Because our inputs comes from a CSV, here we can use the generic Python CSV reader to read this addresses sanfrancisco.csv. We skip the header and read all the records. And then we can call the insert row on the origins and also on the destinations with the same data. Next, we solve our OD. And once our solve succeeded, we can export all the result back into a CSV. And to do that, we first use the generic Python CSV writer. And we write our headers. The headers would be origin OID, destination OID, total time, and total distance. So the thing we want to get is from origin 1 to destination 2, what is the total time and total distance? So we can open a search cursor on our output lines and getting the fields for the fields that we care about. And then we can write the result back into the CSV. So here we have a logic here. If the origin OID and destination OID is the same, we know it's the same inputs, essentially the same stop. So the total time and total distance would be 0, so we skip writing it. So when we get back our result, it's our lines.csv file that we generated. And from here, we can see our from origin 1 to destination 42, what is the total time and total distance. And we generate this for all the stop pairs. Okay, back to you, Melinda.
Thank you, Max. Now I'm going to talk about a few tips and tricks for improving your analysis. Max has talked about this one a couple of times. Unlike the old arcpy.na workflows, actually, not quite. I'll tell you about that one in a moment. So first of all, unlike the old arcpy.na workflows, arcpy.nax gives you control over the units that your results are reported in. You can use the time units or distance units properties to specify which units you want. Behind the scenes, Network Analyst calculates the results using the impedance attribute associated with the travel mode that you selected, but then it converts the units of that impedance attribute into your desired output units before reporting the results to you. And you saw this in one of Max's previous demos. Okay, so here's the one that Max has mentioned a few times. This tip is a performance improvement. You should use a network dataset layer instead of a catalog path to a network dataset in your script. If you use a catalog path, the script has to open the network dataset behind the scenes every time it references that catalog path. And this can be especially slow if you're using licensed data or data on a UNC path. If you instead use the Make Network Dataset Layer tool to open the network once and then pass in that layer by referring to the layer name in other tools and methods that use the network dataset, that can give you a bit of a performance improvement. Okay, let's transition to talk about the Network Dataset class, which is another class on the arcpy.nax module. So recall from earlier that underlying all network analyst workflows is a network dataset. This is the dataset that includes street features and also attributes describing travel times and distances, restrictions for travel, etc. When you perform an analysis, you have to choose which network you want to use to perform the network analysis calculation. arcpy.nax has a network dataset class that allows you to access the network dataset properties and components. You can get some basic information, such as whether or not the network dataset is currently built. But more interestingly, you can access the network's edges, junctions, and turns and get information about attribute values and connectivity for each one. You can iterate over the edges, junctions, and turns and use this to construct your own network analysis to solve problem types that are not available in the Network Analyst Extension. So here's a representation of the network dataset class. The edges, junctions, and turns methods are the most important. Each of these returns a cursor object so you can iterate through all of the network dataset's edges, junctions, or turns. When you call the method, you can specify which properties and network attributes you want to get the value of. For example, for an edge cursor, you can get information such as the from junction and to junction, which are the IDs of the junctions connected at either end of the edge. You can also get the values of network attributes, such as restrictions or impedance values, like the travel time, for that edge. So how could you use this functionality? You can construct a network dataset in ArcGIS, and then you could use the network dataset class to export the network graph to other formats. You can use the network graph if you're writing your own graphing algorithms or using graphing algorithms available in other libraries, such as the third-party NetworkX package. To see an example of this, you can download the Find Network Subgraphs tool. This is a sample script tool that we created that uses NetworkX, and it helps you to identify areas of your network dataset that are disconnected from the rest. It does this by exporting the network dataset graph into a NetworkX graph, and using NetworkX's connected components method to find the subgraphs. So now I'll hand it over to Max, and he'll show you a simple example, and then he'll show you that Find Network Subgraphs script, which is a little bit more complicated.
Okay, thank you, Melinda. So I have two samples to show here for using the Network Dataset API. So the first one goes through all my edges in my network dataset and counts the network edges distance and gets a total edge count and one-way edge count. So let's get it started. So to use the Network Dataset API, first you initialize the Network Dataset object. Here we are also using the Network Dataset layer. And then we have a little bit setup here to do our counting. And all the magic happens here. So this iterator, we are iterating all the edges in the network dataset, get the meters and get the one-ways. And we sum up the total distance. And then we count the edges. And if this edge is a one-way, we count it separately. So here on the right side, in our terminal, we can see the total network edge distances is 12,000 kilometers, roughly 7,500 miles. So what does this mean? If you ever want to do an experiment and want to drive to all the streets in San Francisco back and forth with all the directions that the streets supported, this is the kind of mileage you will put on your car. And then for the total edge count, it's 108,000. And for the one-way edge count, it's 18,000. And it's roughly about 17%. But you couldn't see that it's 17% of all the streets in San Francisco is one-way, because this is different than the classic one-way. This also includes the directed freeway segments. And this edge count is also pretty much twice the amount of streets in your San Francisco network dataset. And the reason is because edge is directional, and the streets is not directional. So for the next demo, we are actually having a script tool to show. So one of the scenarios some of you guys might run into is you want to find out whether the network dataset is fully connected or not. Does it have islands or disconnected portions? This is what our sample is going to do here. So Melinda wrote this tool to help you find all the islands and disconnected portions in your network dataset. This is a simple QA tool for your data. So you will get this network subgraph toolbox if you download the slides and go to the URL. And within there, we have the Find Network Subgraphs script tool. Open it up. It takes in a network dataset. Here we are picking the San Francisco network dataset and get it running. And while it's running, let me explain the code to you. So the first thing it does is it imports the network X that Melinda mentioned. Then we initialize our network dataset's object. And this tool requires the network dataset to be built, so we check whether it has been built. And then here we have a little bit setup here. And what it essentially is doing is creating a temporary table to store your subgraph information. And this is the important part. We're initializing the network X multigraph object, because this is a graph object that we are using the connected components analysis. And next, we iterate through all the edges in your network dataset. Get the source ID, source OID directions from junction and to junction from your network dataset. And once you get those information, you can call the graph that you initialized using network X, call the add edge. And this, what does this mean? So this essentially turns our network dataset and builds a graph in the network X graph model from our network dataset using our network dataset information. So this transforms our network dataset into a network X graph network dataset. Once we get our graph, we can call the network X connected components analysis on the graph. And if the number of components is 1, then that means everything is connected. And if it's not 1, the rest of the code is just to get the subgraph ID on the feature class so we can visualize it on the map. So here, let's visualize our result. So in San Francisco, all the gray area means they are connected, and all the red area means they are disconnected. And let's zoom in. Because our San Francisco data comes from a much larger network dataset, so we have these disconnected bits around the border of this network dataset. So you might find this tool handy for some of your QA, but note, it doesn't really test all the connectivity of your network dataset. Because inside the street network, you could have intersections that are not connected fully like you want, even though they are still accessible from other ways. So this is helpful for you to find the islands, but it's just not fully testing all the network connectivity. And also, because network X stores all the graph in the memory, so you probably can do this analysis in a small network dataset like here in San Francisco, but you wouldn't be able to do it in a nationwide network dataset, for example, North America. But the important idea we are trying to convey here is now it is possible to take your network analysis, export the network dataset in particular, export the information into another system, and then make use of the algorithm that are available in the other system. So back to you, Melinda.
Thank you, Max. Now we'll switch gears a little bit and we'll talk about the ArcGIS API for Python and how to use this for performing network analysis. The ArcGIS API for Python is a Pythonic API for working with ArcGIS Online or ArcGIS Enterprise services. To use this, you don't need ArcGIS Pro on your machine because it works entirely through web services. It's also designed to work very nicely with Jupyter notebooks. The ArcGIS API for Python includes network analysis capabilities that can be accessed in more than one way, though through the network.analysis methods and through the features.analysis methods. These do very similar things. The network.analysis methods are faster and give you access to the full range of network analysis capabilities. The outputs are feature collections only. The features.analysis methods are designed for WebGIS workflows and can use feature services or feature collections for inputs and outputs. We aren't going to go into this in great detail for this presentation, but we did want to give it a mention. And for more information, we suggest that you do the tutorials. There's a link in the slide here. There's also a couple of other workshops at Dev Summit this year that cover some other aspects of the ArcGIS API for Python. They probably won't be doing any network analysis, but it can help you to get started with the API in general so that you'll be ready to tackle those tutorials. I'll hand it over to Max now, and he'll give you a quick demo of doing network analysis with web services using arcgis.features.analysis.
Okay, thank you, Melinda. So Melinda mentioned ArcGIS Python API is easy to use with Python Jupyter Notebook. So in this demo, I'm going to show you how to use the Python API to do a route analysis using the Python Jupyter Notebook. So because the Python API is designed to work with services, so the first thing you need to do is to initialize your GIS object using a portal URL. It could either be your ArcGIS Online or your enterprise portal URL. And here we are initialized with only username, so it knows we need to type in the password. So this is also an important trick if you want to demo this thing to other people. You don't want to put your hardcode, your password into your Jupyter Notebook. Then we search for the San Francisco store and customers from our ArcGIS Online. So let's take a look at our input data. So here, all the pentagons means the stores that in San Francisco. And all the dots represent our store locations. And the color suggested this store, this customers goes to this store. And then we get our customers and stores from our feature service. And let's take a brief look at our data. So our customers, it has a store ID to associate the customer with the store. And our stores, it has a store ID to do the association as well. So what we are trying to solve here is we want to connect to each of the customer with their stores. And we want to use straight line to connect the customer to the store because we want to build a spider diagram. But underlying, we want to use network analysis to calculate the distance and time based on the network distance from each customer to their store. What is the total distance and what is the total time? So what we can do is we can use the connect origins to destinations using ArcGIS feature analysis. So the origin layer would be our stores. The destination layer would be our customers. For the measurement, because we want to use network analysis to calculate the total time and distance, so we want to use a travel mode. Here we are using a driving time travel mode. For the ID field on the origins and destinations, we are using the store ID to associate its customer with the store. And we give it the output name. And for the route output shape, we want to still be a straight line so we can do the spider diagram. So once we get our result back, we can add it on the map in San Francisco. So here is the map showing San Francisco. And we can add our route to this San Francisco map. Wait for it to come up. My network connection probably isn't very good here because I'm on the Wi-Fi. So now it shows up. So here it shows a straight line between each customer to their store. And if you click on one of the lines, you will see it calculates the total time and distance using network distance. It calculates the driving time, the driving distance in kilometers and miles, and also the driving time in minutes. So this demo shows you a simple workflow, how to use the ArcGIS Python API to do analysis. This might be something you are interested if you don't have ArcGIS Pro installed. So back to you, Melinda.
Thank you, Max. Let's just give you a bit of a wrap-up now. So to summarize today's presentation, the arcpy.nax solver objects are great for performing network analysis in ArcGIS Pro in Python. You can use them with either local data or with a service, and you can use it to write scripts and script tools, and this is what we really recommend for doing in Python in ArcGIS Pro. The arcpy.nax.network dataset class can be used to access the network graphs and really extend the network analysis capabilities if you want to. And then arcgis.network.analysis or arcgis.features.analysis can be used to perform network analysis using web services without ArcGIS Pro. Here again is that link to the slides and code for today's presentation, and also a link to the arcpy.nax documentation where you can take a look at some examples and hopefully get started. Thank you very much.
Thank you for listening.